Dear students, welcome to second PUC physics class. In part 1, you have studied electric field and charges, electrostatic potential and capacitance, and current electricity. And the next chapter is moving charges and magnetism. Before going into the chapter, let us study about some basic concepts. That is, what is magnetic field? What do you mean by magnetic field? What do you mean by magnetic field? To understand this concept, consider one magnet, bar magnet. I hope that all of you have seen a bar magnet, right? A bar magnet is having two poles, north pole and south pole. So, this is a bar magnet. So, if you have another bar magnet, or if you consider another bar magnet, and if you place this bar magnet, second bar magnet, near to this first bar magnet like this, then these two bar magnets will attract each other, because we know that always unlike poles attract each other and like poles repel each other. So, here we are not placing any bar magnet near to this bar magnet, we are just placing one iron nail near to this magnet. So, you just imagine that there is one nail and we have placed that nail very close to this bar magnet, and we will see that this bar magnet is attracted towards this, this nail is attracted towards this bar magnet. Who is experiencing or who is exerting force on this nail? Because there is no physical contact between this bar magnet and the nail. Still it is experiencing force. And the question is, who is exerting force on the nail? For that, you have to study magnetic field. What is that magnetic field? So, around this magnet, around this bar magnet, due to this bar magnet's characteristic, it exerts an effect around the space. So, every magnet exerts an effect around the space. Okay? This space is called as magnetic field. So, every magnet has this effect around the space. When you place this iron nail in this field, so this iron nail will experience force. Who is exerting force on this nail? This magnetic field is exerting force on the nail. Due to that force, this nail is attracted towards the magnet. So, the space around the magnet in which the object experiences that effect is called as magnetic field. So, every magnet has this property. It is similar to the electric field. In case of electric field, for electric field you should have one charge, right? So, you just imagine that this is a static charge. When we place a static charge in the space, this charge will create an effect around the charge. Around this charge we have an effect. This charge will create an effect around the charge, and that effect is called as electric field. When you place another charge in this field, if you place another positive charge in this field, this charge will experience the electric force. Who is exerting the electric force? This electric field is exerting the electric force. So, this is about electric field. Here we are considering a stationary charge. Okay, so this is about the electric field. So, this is the magnetic field. So, around the magnet we have an effect, and that effect is called as magnetic field. So we have seen electric field. Similarly, we have seen gravitational field. What do you mean by gravitational field? We know that Earth attracts every body towards itself. Around the space, that means around the Earth, we have one effect, and that effect is called as gravitational field. Here we have a field and the name of the field is gravitational field. So this gravitational field attracts every body having mass towards itself, and the force experienced by the gravitational field is called, or the force exerted by the gravitational field is called as gravitational force. Here this mass is attracted towards the earth because of the gravitational field. So this is about the gravitational field and the electric field. Like electric field, here we have magnetic field. Let us see what are the properties of this magnetic field and who invented this. In the year 1820, a scientist, and the name of the scientist was Oersted. He was in his lab and he was doing one experiment regarding the current. So he had one conductor and the conductor was connected to the main power supply, and he was passing current through the conductor and he was observing something with this apparatus. By mistake, there was one magnetic needle near to this setup. So magnetic needle, so the magnetic needle is like this, and here also we have two poles. Usually it is used to find the direction. So for navigation purpose we are using this magnetic needle. So it was there, unknowingly it was kept near this whole setup. He was doing experiment with this conductor. When the switch is on, current flows through the conductor. When current flows through the conductor, he observed that this magnetic needle which is kept near to this conductor shows deflection. When current flows through the conductor, this magnetic needle shows deflection. So he reversed the direction of current. If the magnetic needle deflects in this direction, when he reverses the direction of current, the orientation of magnetic needle is also reversed. Earlier the deflection was like this. When he reversed the direction of flow of current, the deflection was like this. When he brought this magnetic needle close to this conductor, he observed that the deflection is more. When it is taken away from the conductor, the deflection is less. So he was surprised, because the question is, who is exerting force on this magnetic needle? Magnetic needle will deflect only in the presence of magnetic field. Here we do not have any other magnet close to this magnetic needle, but still it is showing deflection. That means something is exerting force on this magnetic needle, or there is magnetic field around the space. But who created that magnetic field? The question is, who created the magnetic field by which this magnetic needle deflects? And later he found that the charges flowing through the conductor, when the charges flow through the conductor, flow of charge is nothing but the electric current. When charge flows through the conductor, around the space it creates an effect. That effect is called as magnetic field. So whenever charge flows through the conductor, around the conductor we have magnetic field. We have one effect, and that effect is nothing but the magnetic field. Due to that field, this magnetic needle shows deflection. So, he unified electricity and magnetism. They are not two separate characters, they are unified because flow of charge creates an effect around the space, and that effect is nothing but the magnetic field. So, when this magnetic needle is placed in that magnetic field, this shows deflection. So, the moving charges creates magnetic field. So, electric current is the source of magnetic field. So, what is the source of magnetic field? Electric current is the source of magnetic field. So, like electric field, magnetic field is a vector quantity. Electric field is denoted by the symbol E. It is a vector quantity. So, in vector form, E vector. So, magnetic field is denoted by the symbol B. It is also a vector quantity. Magnetic field is represented by B. Electric field is represented by E. Since it is a vector, it has magnitude as well as direction. Always remember, electric field or the magnetic field which is going into the plane of the paper is depicted by a cross. If you find cross mark somewhere, then that means the magnetic field is going into the plane of the paper. So, this is a plane. If the magnetic field is going into the plane of the paper, then that magnetic field is represented by a cross. If the magnetic field is coming out of the plane of the paper, then it is represented by a dot. So, this is the difference between cross mark and a dot. If the magnetic field is going into the plane, then it is depicted by a cross. If the magnetic field is coming out of the plane, then it is represented by a dot. So, this is very important. This notation is very important. Okay. So, cross and a dot. Now, let us see what do you mean by magnetic force. Magnetic force. So, for that consider one field, magnetic field. Cross mark represents magnetic field is going into the plane of the paper. So, here there is magnetic field. When the charge enters this magnetic field, when a charge enters this magnetic field, in order to have magnetic field, the charge should move. There must be flow of charges, then only we can have magnetic field. If a charge is at rest, then we have only the electric field, magnetic field is 0. So, the necessary condition to have magnetic field is the charge should have velocity. So, you just imagine that there is one charge which is moving with the velocity v. Let v be the velocity of the charge. Q is a charge which is moving with the velocity v, and suddenly it enters the magnetic field. So, this is the charge Q moving with the velocity v. Velocity is a vector quantity, so it should have one direction. So, this is the direction of velocity v vector. So, after t seconds later, it comes here, the charge comes here. Now, the direction of velocity is like this. After few seconds later, the charge will come here, its velocities, direction of velocity is like this. So, the particle will move like this. It will follow a circular path. Why this is happening? Because this is the direction of velocity So here the direction of velocity is like this. So this is the direction of velocity at this point. So this is the direction of velocity. Force is a vector quantity. So vector quantity means it is having both magnitude as well as direction. Direction of the magnetic force is represented using one rule, and that rule is called as Fleming's left hand rule. To denote the direction of magnetic force, we have one rule, and that rule is called as Fleming's left hand rule. So Fleming's left hand rule. So to understand Fleming's left hand rule, what you have to do? You have to stretch the first 3 fingers of your left hand like this. Stretch the first 3 fingers of your left hand like this, and you should remember that these 3 fingers should be perpendicular to each other. All the fingers should be perpendicular to each other. So like this you have to place. So always this forefinger gives the direction of magnetic field. Magnetic field is a vector quantity, so this forefinger gives the direction of magnetic field. So this middle finger gives the direction of velocity. This gives the direction of velocity, this gives the direction of magnetic field, and the thumb gives the direction of magnetic force. So always remember, 3 fingers are perpendicular to each other. You should keep your fingers like this, okay, left hand first 3 fingers. So forefinger gives the direction of magnetic field, middle finger gives the direction of velocity, and the thumb gives the direction of magnetic force, okay. So here in this example, magnetic field is represented by a cross. That means magnetic field is going into the plane of the paper. So magnetic field, so this finger, you should keep this finger like this. So because the magnetic field is going into the plane of the paper, so this is the magnetic field. Velocity, this represents velocity, middle finger represents velocity. So it is like this, and this gives velocity. So you should, the middle finger should be like this, okay. So now thumb gives the direction of magnetic force. So the direction of force is upwards. That means the magnetic force acting on this charge is in the upward direction. So this is the direction of force. When the charge comes here, okay, it moves like this. So this is the direction of velocity. So this is the direction of velocity. What is the direction of magnetic force? So this is the direction of magnetic force. So the force is like this. So this force and the velocity, they are perpendicular to each other. Magnetic field is like this. All the 3, F, B and V, all are perpendicular to each other. So this is magnetic field. So this is V, this is F. Right? When the charge comes here, so this is the magnetic field, this is the direction of, this gives the direction, middle finger gives the direction of velocity. So the force is directed towards the center. So this is the direction of force. So always the magnetic force is directed towards the center. So here the magnetic force acts as the centripetal force. Always remember, this magnetic force changes only the direction of velocity. Magnitude of velocity remains constant, whereas in case of electric field, electric force changes velocity. It can accelerate the charge or deaccelerate the charge, but here only the direction changes, magnitude remains the same, okay, under the influence of magnetic force. To understand the direction of force, you should remember Fleming's left hand rule. So, using Fleming's left hand rule, we can find out the direction of magnetic force. Always thumb gives the direction of magnetic force. This gives, middle finger gives the direction of velocity, and the forefinger gives the direction of magnetic field. If this, or if the particle is moving like this, then this is the direction of velocity, this is the direction of magnetic field, this is the direction of force. Okay. So, this is when the magnetic field is going into the plane of the paper. So, this is Fleming's left hand rule. So, in order to understand Fleming's left hand rule, you have to stretch the first 3 fingers of your left hand like this. All the 3 fingers should be perpendicular to each other. So, this is left hand rule. Forefinger gives the direction of magnetic field, middle finger gives the direction of velocity, and the thumb gives the direction of magnetic force. Now, let us see what is the expression for magnetic force, or what is the expression for the force experienced by a moving charge in the presence of magnetic field. So, the magnetic force F, force is a vector quantity, so F vector, since it is a magnetic force is directly proportional to Q. If Q is more, F is also more. Let us consider only the magnitude. This F is directly proportional to velocity. If a particle is having more velocity, it will follow, or it will have a short circle. It will move like this, because the force on the particle is more. If velocity is more, force acting on the particle is also more. If velocity is less, if the particle is moving slowly, then so this is the path taken by the particle. If the velocity of the particle is very, very less, then this is the path taken by the particle. That means, if velocity is more, then the force acting on the particle is also more. They are directly proportional to each other. So, F is directly proportional to velocity. Similarly, F is directly proportional to B. That is, if the field strength is more, then the force acting on the particle is also more. So, from these 3, we can write F is directly proportional to Q, V and B. But velocity is a vector quantity, magnetic field is also a vector quantity. Therefore, you have to write F is equal to Q into V cross B. You have to take the cross product of velocity and the magnetic field. We know that A cross B, cross product of 2 vectors, A cross B is equal to AB sin theta. So, here F is equal to, it is a vector quantity. So, F is equal to Q. Here instead of A and B, we have V and B. So, VB sin theta into n cap. N cap is a unit vector. So, this is the expression for magnetic force. Magnetic force F is equal to Q V B sin theta into n cap. Q is a charge, V is a velocity, B is a magnetic field, and theta, what is theta? Theta is the angle between velocity and the magnetic field. The angle between these two is represented by theta. Okay? So, F is equal to Q V B sin theta. In terms of magnitude, if we consider only the magnitude, then the magnetic force F is equal to Q V B sin theta. Theta is the angle between velocity and the magnetic field. Okay. So, in the presence of electric field, so if this is the electric field is represented by E. If this is the electric field and we have placed one static charge here, in the electric field we have one stationary charge. So, this charge will experience electric force. And what is the expression for force experienced by a charge in the presence of electric field? F is equal to Q into E. F is equal to Q into E. So, the direction of force and the direction of electric field, they are always same. If this is the direction of electric field, then this is the direction of electric force. They act in the same direction. Okay? So, F is equal to Q into E. This is the expression for force acting on a static charge in the presence of electric field. So, this is the expression for force acting on a moving charge in the presence of magnetic field. In the presence of both, or if a particle is moving, if a particle having charge q and it is moving with the velocity v in the presence of both electric field as well as magnetic field, then the total force acting on the particle is F, which is nothing but the force due to the electric field plus force due to the magnetic field. What is the expression for force due to the electric field? F is equal to Q into E plus what is the expression for force due to the magnetic field? Q into V cross B. So, this is the expression for force acting on a moving particle in the presence of both electric field as well as magnetic field. So, this is also known as, this expression is also called as the expression for Lorentz force. Lorentz force. What is the expression for Lorentz force? So, Lorentz force F is equal to Q into E plus Q into V cross B. So, this is the expression for force in the presence of both electric field as well as magnetic field. So, this is the expression for magnetic force, this is the expression for electric force. Becomes equal to 0. We know that the magnitude of magnetic force F is equal to Q V B into sin theta. So, this is the expression for magnetic force. If theta is equal to 0, if theta is equal to 0, sin 0 is equal to 0, 0 into QVB is nothing but 0. So, F is equal to 0. That means, if the direction of velocity of the particle and direction of the magnetic field, they are parallel to each other. If this is the direction of magnetic field and velocity of the particle is also in the same direction, that means if they are parallel to each other, both are in the same direction, then theta is equal to 0, angle between the two becomes equal to 0, because both are moving in the same direction. So, theta is equal to 0. If V and B are in the same direction, or if V and B are parallel to each other, then theta is equal to 0, sin 0 is equal to 0, F is equal to 0. That means, no force acts on the particle. Magnetic force acting on the particle is 0 when they are moving or they are parallel to each other. If V is equal to 0, V is equal to 0 means velocity of the particle is 0, that means the particle is at rest. If the particle is at rest, then F is equal to 0. No force will act on the particle. Magnetic force will act only when the particle is having some velocity, or F is not equal to 0 when the particle is moving. For the particle which is at rest, magnetic force F is equal to 0. If B is equal to 0, then also 0. If theta is equal to 90 degree, sin 90. So, this is the maximum value for sign. Sin 90 is nothing but sin 90 is equal to 1. So, in that case F is equal to B Q V into 1, no need to write it. So, F is equal to B Q into V. So, the magnetic force acting on the particle is, or acting on the charge is maximum when angle between magnetic field and the velocity is 90 degree. When theta is equal to 90 degree, magnetic force acting on the moving charge is maximum. So, F is equal to B Q into V. If theta is equal to 0, F is equal to 0. If V is equal to 0, F is equal to 0. If theta is equal to 90 degree, then the force acting on the moving charge is maximum. When the magnetic force is maximum, when the angle between magnetic field and the velocity is 90 degree. When they are perpendicular to each other, magnetic force acting will be maximum, and this is the expression for magnetic force. So, from this expression F is equal to BQV, or B is equal to, in terms of magnitude of magnetic field, B is equal to F by Q into V, right. B is equal to F divided by Q into V. What is the SI unit of force? SI unit of force is Newton. What is the SI unit of charge? Coulomb. What is the SI unit of velocity? Meter per second. So, the SI unit or the unit of magnetic field is Newton per Coulomb second per meter, or Newton second per Coulomb per meter, or this is also called as Tesla. So, SI unit of magnetic field is Tesla. SI unit of magnetic field is Tesla. Either you have to write like this or like this, Tesla, and it is represented by capital letter T. When B is said to be 1 Tesla, B is equal to 1 when F is equal to 1 Newton and Q is equal to 1 Coulomb and V is equal to 1 meter per second. How to define 1 Tesla? Magnetic field is said to be 1 Tesla when a unit charge, or when a 1 Coulomb charge which is moving perpendicular to the magnetic field with the velocity 1 meter per second experiences a magnetic force of 1 Newton. B is equal to 1 when a 1 Coulomb charge moves perpendicular to the magnetic field with the velocity 1 meter per second, and which if it experiences, when it experiences a force of 1 Newton, we will have B is equal to 1 Tesla, and the SI unit of magnetic field is Tesla or T. So, this is about the magnetic field and the magnetic force. Take down.